Piezoelectric type accelerometers were the first commercial ones sold, so it behooves us to explain how the piezoelectric effect works. The effect is normally described as the generation of electric charge within a crystal when the crystal is subject to mechanical stress. However, as we will see in the next slide, redistribution is a better description than generation. The piezoelectric effect occurs in natural crystals such as quartz and topaz, in man-made ceramics such as barium titanate and lithium niobate, and in the plastic PVDF. It was discovered by the French scientist brothers Jacques and Pierre Curie in 1880. At the time, it was just another scientific curiosity. It was not used commercially until the development of sonar systems in World War I. Later on, the piezoelectric crystal became the core technology for sparking systems in gas burners and cigarette lighters. Today, you find them in actuators, valves, microphones, speakers, amplifiers, and of course, accelerometers. In this simple model of the piezoelectric effect shown in this diagram, a quartz crystal is modeled as a helix with repeating single silicon and dual oxygen atoms. This view is a cut of the crystal as seen along the axis of the helix. In a single crystal cell, there are 3 atoms of silicon and 6 oxygen atoms. Each silicon atom has 4 positive charges, and each O2 pair carries 4 negative charges. With no mechanical stress, each quartz cell is electrically neutral. When an external compressive load is applied, however, the lattice deforms, shifting atoms inside. The positive silicon ion is pushed to the top and the negative oxygen ion is pushed to the bottom. You get an electric charge imbalance along the y-axis. When a tensile load is applied, you also get an electric imbalance along the y-axis, but in the opposite direction. You get negative charge on the top and positive charge on the bottom. You can't measure the piezoelectric charge unless you attach conductive electrodes to both ends of the crystal. When you do this, your piezoelectric crystal becomes a capacitor with a dielectric material in between the plates. The dielectric material is the crystal itself. The voltage across the electrodes is proportional to the force in the crystal. Because the electrodes equalize charges along the surface, the piezoelectric crystal cannot normally detect a force direction. If electrodes are formed with a complex pattern, you can determine the location of the applied force by measuring the response from a selected electrode. A piezoelectric sensor is a direct converter of a mechanical stress into electricity. The piezoelectric effect is reversible in that voltage applied across the face produces mechanical stress in the crystal. Let's look at some simple equations that describe the piezoelectric voltage. The constant D11 represents the charge output along the x-axis of the force along the x-axis. The units of measurement are coulombs per Newton. The voltage is the charge Q divided by the capacitance C. The middle equation at the bottom is the standard equation for a capacitor. And when you combine the equations, you see that the voltage output on the electrodes is directly proportional to the force Fx along the x-axis of the crystal. Piezoelectric type accelerometers were the first commercial ones sold. In this diagram, the piezoelectric crystal is sandwiched between the proof mass and the base. The acceleration of the proof mass exerts a force on the crystal. The crystal is extremely stiff, so an external spring is not needed in the system. The damping within the crystal is small, but the natural frequency of the crystal is so high that we can still sense a wide frequency range. The piezoelectric accelerometer has a very rugged construction. No drift, and with no internal electrical resistance to worry about, it can be used at high temperatures. When it was first invented, people liked its small size, but with today's miniaturized electronics, the package size is considered large. The original piezoelectric accelerometers used quartz for the sensor element. Quartz has the best long-term stability, It does not exhibit the piezoelectric effect. This means the quartz does not generate spurious voltage from this effect when heated or cooled. On the downside, quartz has lower charge output than ceramics and high open circuit voltage sensitivity. Its biggest disadvantage is that it can only be cut in certain geometries, limiting the designs of the sensor. I suppose this problem is similar to producing diamond jewelry, but at a heck of a lower cost. Ceramics can be machined or molded into a variety of plates, beams, and annular rings, which are then polarized to produce the piezoelectric effect. This provides good dimensional flexibility. They also have very high charge output, compatible with microelectronic charge amplifiers. Ceramics are piezoelectric with a relatively high temperature coefficient compared to quartz. Other than for some expensive and highly specialized ceramics, this limits their usage to smaller temperature ranges than for quartz. The original designs for accelerometers were of the compression mode type. In this simple design, a quartz crystal or ceramic element was preloaded with a seismic mass. The sensors had high sensitivity and high natural frequency, providing a broad usable frequency range. However, the design was sensitive to strain in the base, and various tweaks over the years could not eliminate this problem. Hence, this type of design was replaced by other geometries. In Flexure Mode, the crystal bends around a central fulcrum, with compressive strain on the bottom and tensile strain on the top of the crystal. You get very high sensitivity in a small, low-cost package. However, the design is fragile, especially under shock loads. It is used today only for very short sensors. In Shear Mode, the piezoelectric crystals are mounted radially around a fixed center post. A seismic mass is mounted outboard of the crystals. The crystals have shear forces acting on them during acceleration. The sensor is held together by adhesive screws or metal bands. In a tri-shear sensor, 3 elements are positioned at 120-degree angles around the center post. The Shear Mode design isolates the crystal from base strain inputs, while still providing the same degree of sensitivity as the compression mode design. As such, most piezoelectric accelerometers sold today use Shear Mode. Let's look at this commercial Triaxial Shear Mode accelerometer. The 3 ceramic elements are held in place by a clamping ring that isolates them from the effects of base strain. The transfer function is flat until 12.6 kHz, as the sensor has a resonance frequency at 42 kHz. Piezoelectric accelerometers generally have wider frequency response than capacitive or piezoresistive ones. Both the maximum and minimum mounting torques are specified. Too little torque, and you won't transmit the vibrations of the structure to the accelerometer. Too much torque, and you will preload the ceramic elements and produce false readings. The sensitivity of a piezoelectric accelerometer is shown in picocoulombs per G. This is not a great deal of charge. The only way to measure it is to feed the signal to a charge amplifier and read the voltage output. The sensor can measure acceleration up to 6,000 Gs, far higher than the capacitive or piezoresistive types. The accelerometer will pick up a small amount of transverse vibrations when measuring vibration in its axial direction. This is shown in the diagram on the right side of this slide and in a specification called Max Transverse Sensitivity. This spec is typically measured at only one frequency, which is 30 Hz in the case of this sensor. This means that the axial acceleration that you measure will be a combination of both the axial and transverse accelerations. As an example, suppose the actual axial acceleration were 5 Gs, which would be a charge of 5 picocoulombs, and the transverse acceleration were 1 G, which would be 9.8 picocoulombs. At a transverse sensitivity of 4%, the accelerometer would tell you that the axial acceleration is 5.04 Gs, not 5 Gs. The sensor operates between -74 and 250 degrees C, with a temperature coefficient of sensitivity of only 0.05% per degree C. The sensor can withstand a shock of 20,000 Gs, which is an enormous number. Even with the miniaturization of accelerometers and their integration into electronic systems, piezoelectric accelerometers are still sold in high quantities. The capacitive and piezoresistive accelerometers cannot handle such high temperatures or levels of shock and acceleration without permanent damage. Let's recap. Now you've seen how early mechanical accelerometers were designed and built, and why they're still used today. Let's study common designs put into MEMS format.